In this video, we will continue looking at cycloalkane conformations. We'll be focusing on cyclohexane that is substituted with 2 or more substituents. But before we move forward, I want to remind you about conformations compared to stereoisomers, because in this video, we will be talking about both of them. So with isomers, we are talking about the same molecular formula but different compounds. We have constitutional isomers that have different connectivity, or stereoisomers, where we have the same connectivity but a different arrangement in space. With conformations, we're talking about the same molecule, so of course it has the same connectivity and a different arrangement in space. So how do conformations differ from stereoisomers? Well, the big difference is that with stereoisomers, they cannot be interconverted because they are different compounds, whereas conformations can be interconverted by rotation around single bonds. So they are just different arrangements of the same compound. So here we will be looking at different conformations of different stereoisomers. So our first compound is cis-1,2-dimethyl cyclohexane. The name is bigger than the compound. And then over here we have trans 1,2-dimethyl cyclohexane. So with cis, both groups are on the same side. Here they're both coming forward. And trans, you have one group coming forward and one group going back. So let's look first at cis-1,2-dimethyl cyclohexane. And we're going to draw this as a chair. So this is carbon 1, carbon 2. I could also go counterclockwise, but whichever way you number it, just make sure that your substituents are 1, 2 rather than 1, 6. I'm going to call this carbon 1 and this carbon 2. So here is my methyl group on the top face and my hydrogen on the bottom face. And then on carbon 2, my methyl group is on the top face, equatorial, and my hydrogen is on the bottom face. As I do my chair interconversion, I'm moving the headrest down and the footrest up. So this is still carbon 1. What was the headrest is now the footrest, and this is carbon 2. Notice, because the way I numbered on the original flat structure, this was carbon 1, and then I went clockwise to carbon 2, we're keeping that the same way, looking at our ring from the top, so that if this is carbon 1, we're going clockwise to carbon 2. This is carbon 1, we're going clockwise to carbon 2. So on carbon 1, we still have our hydrogen on the bottom face and our methyl group on the top face. And at carbon 2, we still have our methyl group on the top face and our hydrogen on the bottom face. So what we started with, we had one methyl group axial and one methyl group equatorial. What we end with, the equatorial methyl group is now axial, and the axial methyl group is now equatorial. Once you do your interconversion, always double check that you still have the groups at the same position. So carbon 1, carbon 2, carbon 1, carbon 2. We are starting out with both methyl groups on the top face, they are cis. We are ending with both methyl groups on the top face, cis. And we also double checked that what was axial is now equatorial, what was equatorial is now axial. It's not helpful to try to analyze the conformations if you have made a mistake in your chair interconversion, so always double check. Now, let's think about the differences between these conformations. On the left, we have one methyl group axial, so that means we have some 1,3 diaxial interactions so we have some van der Waals strain. In our conformation on the right, we again have one methyl group axial, so we have some van der Waals strain. In both cases, we're talking about a methyl group, so the amount of strain in both conformations is exactly the same. And so the equilibrium lies right in the middle. So if we could take a snapshot, we would have half the molecules in this conformation and about half the molecules in this conformation. So the cis 1,2 dimethyl cyclohexanes, both chair conformations are equal energy. Let's take a look then at trans. So again, I will stick with carbon 1, carbon 2, and here my methyl group is up and my hydrogen is down. And then, let me just come back up here, 1, 2, and then carbon 2, my hydrogen is on the top face and my methyl group is on the bottom face. As I do my inversion, I'm moving my headrest down to the footrest. So this is carbon 1 and this is carbon 2. On carbon 1, my hydrogen is still on the bottom face and my methyl is still on the top face. For carbon 2, my hydrogen is still on the top face and my methyl group is still on the bottom face. Let's double check. Methyl group at carbon 1 and carbon 2, methyl group at carbon 1 and carbon 2. This methyl group is on the top face, this is bottom face, so they're trans. This methyl group is top face, bottom face, so they're still trans. This methyl group is axial, it became equatorial. This methyl group is axial, it became equatorial. So it's a good chair interconversion. We didn't make mistakes that way. Now let's think about strain. Remember, because these are chair conformations, we don't have torsional strain or angle strain, so the only possibility is van der Waals strain, and that's what we have if we have bulky groups that are axial. So in our conformation on the left, we have a methyl group axial and another methyl group axial. So that means we have van der Waals strain due to two 1,3 diaxial interactions. And then if we look at the conformation on the right, this is equatorial, this is equatorial. So we only have hydrogens axial, so we have no van der Waals strain. So if we consider the conformation on the left, which has strain, and the conformation on the right, which has no strain, the conformation on the right is more stable. Therefore, the equilibrium lies to the right. That means at equilibrium, we will have more molecules in this conformation than we do in this conformation. All right, now I didn't leave myself much room, but let's consider the energies of the different compounds and of their different conformations. So we're going to draw a small energy diagram, and our y-axis is energy, and the x-axis, we can just think about it as the different conformations, the equilibrium between the two different conformations. So for cis, we're going to do that in red, and we have a little bit of van der Waals strain, so let's just say that this is the energy of the cis conformation on the left, and this is the energy of the cis conformation on the right. Equal energy. Now for trans, we're going to use blue, and the conformation on the left has more van der Waals strain than what we saw in the cis conformations. So that one is going to be higher energy, but the conformation on the right, because there's no van der Waals strain, that is going to be lower than the first one, but also lower than the cis conformations. Here we have no van der Waals strain, so this is lower energy than the other trans conformation, but it's also lower energy than the cis conformations that have one axial methyl group in each one. Now, if we compare the cis 1,2 dimethyl cyclohexane to the trans 1,2 dimethyl cyclohexane, we are actually going to focus on the more stable conformation. In other words, we are comparing either of these to this one. And so what we see is that the trans is more stable than cis. So for 1,2 disubstituted cyclohexanes, the trans is more stable than the cis. It doesn't matter that we have this conformation that's higher energy, because if we're just thinking about trans, we know that more molecules are going to exist in this conformation. So we compare the energy of most molecules in this conformation and essentially all molecules in these conformations. And so for 1,2 disubstituted cyclohexanes, trans is more stable than cis. But before we try to make a rule out of that, let's take a look at other substitution patterns. On this slide, we're going to go more quickly, but you can pause the video to catch up if you need to. So our compound on the left is cis, our compound on the right is trans. So our substituents are at carbon 1 and 3. So this is cis 1, 3 dash dimethyl cyclohexane. And then this one is trans 1, 3 dimethyl cyclohexane. I'm going to call this carbon 1 and this is carbon 3. So here is my methyl group on the top face, hydrogen on the bottom, and then methyl group on the top face, hydrogen on the bottom face. When we do our interconversion, we get carbon 1 has the hydrogen on the bottom face, the methyl on the top. Carbon 3 has the hydrogen on the bottom face and the methyl on the top face. So here we have two methyl groups that are axial, and in the conformation on the right, our methyl groups are equatorial. So the conformation on the left has van der Waals strain due to two axial methyl groups, and the conformation on the right has no van der Waals strain. So the conformation on the right is more stable, which means the equilibrium lies to the right. Looking at our trans stereoisomer, now carbon 1, 2, and 3, we have our methyl group on the top face at carbon 1, and then our methyl group is on the bottom face at carbon 3. We do our chair inversion, and carbon 1 is now the footrest, and carbon 1 has the hydrogen down, the methyl on the top face. At carbon 3, the methyl is down, and the hydrogen is on the top face. So double check the chair, double check the inverted chair, make sure that you did a correct inversion. And then let's assess our conformations. The one on the left, this methyl group is axial, this methyl group is equatorial, so we have van der Waals strain due to one axial methyl group. In the conformation on the right, this methyl group is equatorial, this one is axial, so we have the same amount of van der Waals strain due to, again, one axial methyl group. The only difference is that in the conformation on the left, this methyl group is bumping into the hydrogens that are on the top face, whereas the conformation on the right, this methyl group is bumping into the hydrogens on the bottom face. But it's the same amount of energy, and so the equilibrium lies right in the middle. Next, let's do the same evaluation on an energy diagram. And here we have energy, and then our x-axis is just, we're looking at the different conformations. So for cis, I'm using red, and the conformation on the left is high energy because of van der Waals strain due to two axial methyl groups. And the conformation on the right is low energy because there's no van der Waals strain. And then for the trans stereoisomer, the conformation on the left has some strain, some van der Waals strain, because of one axial methyl group, and the conformation on the right has the same amount of strain. So for 1,3 disubstituted cyclohexanes, the cis is more stable than the trans because cis has one conformation that is more stable than the two trans chair conformations. So with 1,2 disubstituted, trans was more stable than cis, but with 1,3 we have cis is more stable than trans. You can go through this with 1,4 disubstituted cyclohexanes and see which one is more stable. Now you could try to memorize rules about 1,3 and 1,2 and 1,4 and who's the most stable, but it's going to be a lot easier if you can work it out. So go ahead and convert your flat structures into a chair, do the chair interconversion, assess the types of strain, and then figure out the relative energies. So if you like to memorize a million facts, go for it. But otherwise, if you understand it, then you can derive this information as needed. On the last couple slides, we were comparing disubstituted cyclohexanes where both substituents were the same. But what if we have different substituents? Then how do we compare the relative energies of the different conformations? So again, I'm going to go through this quickly, but stop the video and work through the details if you need to. So once again, we're looking at cis 1,2 dimethyl cyclohexane. This is carbon 1, carbon 2. I'm going to make this carbon 1, carbon 2. So here is my methyl group on the top face, hydrogen on the bottom face, methyl group on the top face, hydrogen on the bottom face. When we do our inversion, that gives carbon 1 is here, carbon 2 is here. Our hydrogen is on the bottom face, methyl on the top face, and at carbon 2, methyl on the top face, hydrogen on the bottom face. In both cases, we have one axial substituent. The substituent is the same, and so both conformations are equal energy. So the equilibrium lies right in the middle. How does this change when we're looking at different substituents? So here we have a T-butyl group and a methyl group. So I'm going to call this carbon 1, carbon 2, and carbon 1, carbon 2. So at carbon 1, we have our T-butyl group on the top face and our hydrogen on the bottom face. At carbon 2, we have our methyl group on the top face and our hydrogen on the bottom face. After we do our inversion, this is carbon 1, carbon 2. Carbon 1 has the hydrogen on the bottom face and the T-butyl group on the top face. Carbon 2 has the methyl group on the top face and the hydrogen on the bottom face. So here we have a group axial and equatorial, and in the conformation on the right, we have one group axial and one group equatorial. So is this the exact same situation as what we had above? Not even close, because here we have a methyl group that is axial, so we have 1,3 diaxial strain due to a methyl group that is going to be bumping into this hydrogen and this hydrogen. So we have some van der Waals strain because these atoms are too close to each other. Rather than thinking about this just written as a CH3, let's try to emphasize the size. So hopefully it's more obvious how these hydrogens are going to be bumping into each other. But now if we look at the T-butyl group in the axial position, all right, I'm going to erase the T-butyl group and then redraw it. So here I have a carbon that is connected to a carbon and another carbon and another carbon. So This carbon is sp3 hybridized, so we have a tetrahedral arrangement, but then each of these carbons is sp3 hybridized. So I'm just going to fill in the hydrogens on one of these. So here's a hydrogen and a hydrogen and another hydrogen. Meanwhile, we have on the ring this hydrogen and this hydrogen are axial and on the top face. I'm just going to write these out as a CH3. So now this hydrogen is so close to these ring hydrogens that the amount of van der Waals strain is going to be significant. So in the case of having the methyl group axial, we're going to have van der Waals strain. But in the case of having the T-butyl group axial, we're going to have van der Waals strain. And so because our substituents are not equal, then the strain by having either one of them axial, that's not equal either. So having the methyl group axial is not nearly as bad as having the T-butyl group axial. And so in this case, the equilibrium lies very far to the right. So the molecule will put up with a little bit of van der Waals strain from a methyl group axial to avoid having a ton of van der Waals strain from having a T-butyl group axial. So at equilibrium, almost all of our molecules are going to exist in this conformation with the T-butyl group equatorial rather than having the T-butyl group axial. So again, trying to memorize some relationship about cis, trans, 1, 2, 1, 3, 1, 4 is not really as helpful, but instead being able to draw the chair, the interconverted chair, and being able to assess the relative energy, that is a lot more flexible, and you can apply that approach to different compounds. In the last slide of this video, we're going to continue to look at substituted cyclohexanes. We've already seen mono and di-substituted, but now we're going to look at multi-substituted. We could have cyclohexanes with 3, 4, 5, 6 substituents, and we can analyze them in this way. So let's start out with drawing chairs from our flat structures. So for the first compound, this would be carbon 1, 2, 3, and 4, because numbering in that way gives all of the substituents the lowest number possible. So I'm going to stick with calling this carbon 1, 2, 3, 4, and let's fill in our groups. At carbon 1, we have our methyl group on the top face and our hydrogen on the bottom face. At carbon 2, we have a chlorine on the top face and a hydrogen on the bottom face. And at carbon 4, we have a hydrogen on the top face and an isopropyl group on the bottom face. Let's consider our other chair. So the headrest becomes footrest, the footrest becomes headrest. So this is carbon 1, 2, 3, and 4. At carbon 1, our hydrogen is still on the bottom face and our methyl is still on the top face. At carbon 2, our chlorine is still on the top face and our hydrogen is still on the bottom face. And at carbon 4, our hydrogen is still on the top face and our isopropyl group is still on the bottom face. In our conformation on the left, we have a methyl group axial and a T-butyl group axial, and our chlorine is equatorial. So we have an axial, axial, equatorial. In the conformation on the right, our isopropyl group is equatorial, our chlorine is axial, and our methyl group is equatorial. So we have axial, equatorial, equatorial. So while it might be tempting, we don't automatically want to assume that having 2 equatorial groups and only 1 axial is better, because we really need to consider what are those groups. So let's focus on our biggest, bulkiest group, that is our isopropyl. So having an isopropyl group axial, that is going to bring in a lot of van der Waals strain, whereas having the isopropyl group equatorial, no van der Waals strain. So this conformation on the right is going to be more stable, and so equilibrium will lie to the right. So the molecule will put up with some van der Waals strain due to the chlorine to avoid van der Waals strain due to having an isopropyl group axial. And it's possible to look at values for the energy differences for particular substituents in an axial versus equatorial position to figure out exactly what is the cost, what is the overall energy difference between these two conformations. We're not going to do that in practice, but it could be done. If we look at our next compound, once again, this is carbon 1, 2, 3, and 4 to give all of our substituents the lowest number possible. So carbon 1, 2, and 4. And let's fill in. At carbon 1, our methyl group is on the top face, hydrogen on the bottom. At carbon 2, our hydrogen is on the top face and our T-butyl group is on the bottom face. And at carbon 4, our hydrogen is on the bottom face and our isopropyl group is on the top face. As we do our inversion, then this is carbon 1, 2, and 4. Carbon 1, we still have our methyl on the top face, hydrogen on the bottom. At carbon 2, we still have our hydrogen on the top face and our T-butyl group on the bottom face. And at carbon 4, we still have our isopropyl group on the top face and our hydrogen on the bottom face. So our conformation on the left, we have an axial group, and an equatorial group. And our conformation on the right, we have an axial, equatorial, and equatorial. Keep in mind, so up here, I said that having the isopropyl group equatorial is really, really important. But for this compound, having the isopropyl group equatorial is great, except that that puts the T-butyl group axial. And the T-butyl group is much bigger and bulkier, and so there is a lot more van der Waals strain. So this conformation is going to have a ton of van der Waals strain because of the T-butyl group being axial. On the other hand, this conformation, we have our T-butyl group equatorial, our methyl group is also equatorial, our isopropyl group is axial. But the problem of having the isopropyl group axial is not nearly as bad as having the T-butyl group axial, and so this conformation is going to be more stable, and so the equilibrium is going to lie very far to the right. Even though the conformation on the right has an axial isopropyl group, which has a lot of van der Waals strain, it doesn't have an axial T-butyl group, which has a lot of van der Waals strain. How's that for quantifying? So with the examples that we've looked at, and more importantly with the approach that we used, you can assess any cyclohexanes with different substitution patterns. All you need to do is draw the chair, draw the interconverted chair, and then look for the types of strain, and you can assess their relative stability, which means you can identify which conformation is more stable, and therefore which conformation predominates at equilibrium. You can be quantitative about this, not just a lot versus a lot. You can put numbers to this. You can calculate equilibrium constants using values that are available in your textbook. And so there's a lot more information that can be determined about these, but this is where we're going to leave it for now. Although later this semester, we are going to see some examples where the different conformations and the predominance of one conformation at equilibrium is going to have an impact on reactivity. So even when we finish this chapter, we're not done with this topic.